Hi everyone. Is anybody here? Oh, hello. All right. So I have John in the Twitch chat and Michael in Teams. Is that it? I mean, I can't say I'm overly surprised because I'm over it. I'm sure y'all are too. And I said this stuff isn't on the test on Wednesday. It's on the next test. So, okay, a couple more people turning up. It is not my dog. That's my neighbor's dog. Not even in this building. They're in a totally different building. But their dog barks so loud. I'm pretty sure that's Gil. He's a very cute dog, but he's got problems. Good morning, good morning. There we go. Everybody is sort of getting underway here. I slept through like 10 alarms this morning. So, great. All right. We're ready to talk about some physics. How are y'all doing today? Any questions about anything before we get started? Y'all have test on Wednesday. Homework's up. I'll let you know when I'm doing like review sessions and things. Probably Tuesday evening and then Wednesday afternoon. It feels like you just took your midterm. Oh, by the way, I know a couple of people have asked about when the midterm grade is going to get put into your Canvas course instead of the recitation. I went to do it and found a bunch of errors in the grading. So hopefully your grades will be updated and then you will get it'll get put in today. Canvas has some really weird glitches that we're discovering. It wasn't just you, Dawson. There was a section where it was copying the rubric from the previous person. So like the previous person got like 10 out of 14 and then it would give you 10 out of 14 regardless of how you actually did. And unfortunately the one it was copying was not that good. So yes, hopefully there was about, I think, 4 or 5 people who were getting an updated grade. All right, so today, let's see, agenda for today. Okay, so we've been talking about work. I don't know what day it is. Let me share my screen. Somehow, oh, I have to join the team over here. Forgot. Will the final cover similar questions to all 3 exams? What do you mean by similar? Good morning. Yeah. That's the tricky part. What do you mean by similar? Same concepts, yes. So the final exam is cumulative. That is actually good news because physics is cumulative. So if you think back to like the first week of classes and like the first month or so, it was so easy. It was like, oh, there's Duchess. Can I show you Duchess? Can you see that dog? Maybe. There's a very cute. That's Duchess. Duchess is a Southeastern guide dog. She's a service dog with Southeastern. She's a veteran dog, and she's very old, so she's getting her walk. She's retired. Sorry, I'm just always really happy when I see Duchess. Okie dokie. What was I talking about? Oh yeah, so like the first, it's like vectors and like one-dimensional motion. It's really nice. It's very gentle. So it's cumulative, but that's a good thing. Okay. So we've been talking about work. So let's consider work done by gravity. So let's say you have a person standing in an elevator. Elevator moves 200 meters upward. Starts at rest. Oh, great, the lawn guys are here. Thanks. Not much work. Did gravity do on, I guess you're the person in the elevator. You can tell because you're wearing a cowboy hat. I have to give you your mass, don't I? Your mass is, we're going to say you're 100 kilograms. It's a really heavy hat, cowboy hat. Tell me how much work gravity did on you. So this is stuff that is on the test. So hopefully you know how to do this. Did gravity on you do on you? I'm functional today, mostly. No thoughts? Yes. So John in the Twitch has pointed out it would be negative. Oh, thanks, lawn guy. Great. John says it would be negative because it is working against the motion. You are correct. So if you were to say that on a test, and even if that's like the only thing you say, you would get some points for that because that is true and useful. Can you tell me how much? Trying to remember the equations again. So for work, I can actually pull them up. There's a lot of possible equations. And we talked about them towards the end of class. There was like, oh yeah, these versions, right? So force times distance cosine theta, F dot delta R, the integral of force over distance, and then the line integral of force over some path. So Which of these is probably the most useful for us? I'm thinking the simple one, F delta R cosine theta. That seems like a good choice. Uh-oh. There it is. I don't know how it determines what order it puts these in. I know we're all tired, but someone give me an answer. Not a lot. Is gravity perpendicular in this example? I'm not sure what you mean by perpendicular. Gravity pulls down. So perpendicular to the motion. So which way are you moving? You are moving upward, and the force of gravity on you is downward. So John asked if force is a vector in this case. Force is always a vector, but the question is more, do you have to do that dot product thing? You don't have to, you can. So for example, in this case, your force of gravity would be 0I minus mgj. Your delta R would be 0I and 200 meters upward. If you did the dot product, right, it would be 0 times 0 plus negative mg times 200, which ends up being the same, yes, starting on the correct answer, as if you just did mg times your 200 meters times the cosine of the angle between them, and the angle between them is, computer's being really slow. Cosine of 180, which gives us our negative number. So we have negative, it's so convenient. I don't know what's wrong with my computer, hang on. Oh, there it is. Jeez, why are you so slow? Maybe it's because it hasn't rebooted in like 6 days. Dang it. Yeah, my computer's crashing. But yes, John's answer is correct, if you can see that in the Twitch stream. And then possibly my computer is going to crash. Yes, so John says I made gravity negative 9.8, but you should not do that because cosine provides a negative. That is correct. Cosine is what provides the negative. So for people in Teams that cannot see it, the correct answer is negative 196,000 joules. Okay. Hopefully that will come up. It's been having trouble sending things. God, for God's sake. Yep, computer's frozen. Wonderful day. Okay. While I restart this, can you tell me how much work did the normal force do on you? Can delta R be negative? In this equation, F and delta R are both magnitudes, so they would be positive. If you're doing the vector version, I love it when Task Manager won't even open. Control-Delete. Hard reboot. Great. So delta R in the equation over here, the F delta R cosine theta, F and delta R will always be positive because they're magnitudes. Over here, you could just as easily have a negative 200 meters. That would be the case where the elevator moves downward, right? If the elevator moved downward, gravity would be doing positive work. So we're rebooting. Hooray. Michael forgot that we wanted an angle between them. I thought FG was perpendicular. So FG is perpendicular for things that are moving horizontal. So that's the examples we've been doing so far. But now it's moving vertical. Now we have to, it's not perpendicular anymore. Oh, that was fast. All right, I forgive you, computer. Okay, can you tell me how much work did the normal force do on you? I don't know if you can see that in Teams. It's like, I don't know why it doesn't want to let me use the chat for some reason, but it doesn't. How much work did the normal force do on you? Write it on something and hold it up. So this one is more of a thinking problem than a math problem. Go away, WebEx. Join. Okay. So John says, I presume it would be higher than 196,000 joules because if it were, that you would not move at all. Well, so we have to think about this because if it was 196,000 and gravity did negative 196,000, your net work would be 0. That doesn't mean you don't move. That means your delta K is 0. What was delta K again? Change in kinetic energy. Okay, are we back? Are we working? My pen might still be dead. Nope, pen's working. 9.8 times 200. Both of these equal negative 196,000 joules. Okay, so how much work did normal force do? So here's the key for these types of problems, is for work, you are always interested in from some initial position to some final position. It's going slow, right? So we think about at our initial position, we have a guy standing in an elevator. Doesn't want to let me draw his cowboy hat. I don't know what's wrong with my computer. Right, and our work, whoa. Delta K, jeez. Technology. Okay, delta K is our change in kinetic, what the heck? Energy. Okay, so we start out and then we end up also at rest, still wearing our cowboy hat, but 200 meters higher. So what is our change in kinetic energy in this case? Remember, kinetic energy is 1/2 mv squared. Okay, John has a thought. Does anybody in Teams have a thought? No. Well, John, you're correct. The answer is 0. Delta K is 0, right? Because you're 1/2 mv squared. 1/2 mv squared. 0 both times. So our net work done is going to be 0. Our net work is if we add up the work done by all the forces. The only forces are gravity and normal. So if gravity did 196,000 joules, then our net work done by the normal force has to be positive 196,000 joules. So this feels a little weird for students because you're like, but it sped up and then slowed down and then surely it's doing some work. So we think about the forces, right? So at first, our gravity and normal are equal. And then when we accelerate upward, we're going to have a stronger normal force than the force of gravity, right? Because our net force is upward. And then we're maybe going to coast for a while at constant velocity. And then we're going to slow to a stop. And when we slow to a stop, our normal force is less than gravity, right? This is the bit where you feel heavier. This is the bit where you feel lighter. Hopefully this looks kind of familiar. So normal is doing more work. Oops. No, I don't want to open Chrome. I do want to restore my pages, but I don't want to open Chrome. No, stop opening all my programs. Stop. Okay. So if I looked at the network, like your work done, total work done versus like distance, right? Gravity is just constantly doing work at mg times x the whole time. Sorry, you can't even see this, but it keeps opening millions of windows and it's really annoying. Stop. Okay, whereas your normal force sort of does more work for a while and then does less work, and then they end up doing essentially the same total, but this is like absolute value, right? Because gravity is doing negative work. Does that make sense? All right, normal. If we were to do a better one is force in the y direction for our y direction, this goes to 200, right? Gravity is doing a constant amount of force. This is force of gravity, negative mg, right? So the work done by gravity would be this negative integral, right? Whereas the normal force is going to start out the same as gravity, but positive. Then it's going to be bigger, and then it's going to be the same, and then it's going to be lower, and then it ends up the same. And we do this area. If I had drawn them better, they would be the same. Maybe it's like here. Right. Does that make sense? Same area. Even though normal force is not constant. So this is something to think about when you're doing work problems. Is work, you can always think about just the beginning and the end. And it helps you sort of eliminate all of this sort of, oh, gee, I don't know the curve. I don't know how fast it's accelerating. I don't know any of this. You just know the beginning and end. Okay. So let us consider instead you are launched from a cannon straight up. With enough speed to reach a height of 200 meters. Okay. So you're in a cannon. Pew! Okay, this is your 200 meters. Okay. How much work did gravity do as you flew upward? Same person, mass is 100 kilograms. People in Teams, are you still here? I haven't heard from anyone in a while, which makes me wonder if there's a problem. Okay. Still here? Okay. At the end, I might ask y'all how you feel about doing synchronous versus asynchronous classes, because Corey says, negative 196,000 joules. You are correct. Same amount, because it is the same, same force, same distance. Okay. Are there any other forces doing work? During this flight? We're going to ignore like the cannon for now. Okay. John says no. So our network is negative 196,000 joules. So our change in kinetic energy is negative 196,000 joules, which makes sense that we had some initial velocity, v squared minus 1/2 the initial squared, right? We know v final is 0 because it's 0 when you reach the peak. Yes, you're correct. Normal is only on the ground. So we can use this to find his initial launch speed if we want. So this is a little easier than trying to do it with kinematics. So 96,000 times 2 divided by 100 square root. So I get that he must have been launched at 62.6 meters per second. That's pretty impressive to reach that height. Okay. Hopefully it makes some sense. Okay, so what do we mean by work? So work is transferring energy. So gravity essentially sucked out 196,000 joules of energy. Right? It had some kinetic energy. Gravity did some work and removed it, and then it had no kinetic energy left. Where did it go? Remember that energy can't be created or destroyed. Where did it go? Back into gravity. Yeah, became potential. Okay. It got stored as potential energy. Good. Right. So we have not yet talked about potential energy. What's potential energy? Technically, some of it turned into heat. If we're going to consider air resistance, a tiny amount would turn into heat, or turn into heat dissipative forces. So heat, sound, deformation. Right. Okay. Potential energy. What's potential energy? Energy due to position. Yeah, stored energy. Energy that is stored and can be used to do work later. And specifically for gravity, this is due to position. So this is actually kind of like a battery almost. Many of you might know that one of the concerns about renewable energy is that it's very hard to store, right? There's a lot of concerns about building the best battery technology, and Tesla's like battery walls and things like that. One thing you can do is you can use, like, say, nuclear power or solar power or something that you need to store, and you use it to like pump water up a hill, and then all of your energy is now stored. You want the energy out, you let the water flow back down the hill. So it's stormy weather. Okay. So what do we mean by we can get energy back out? Doing work later. So maybe our guy gets launched up in the air, and right at the very peak, he like steps onto the edge. Maybe there's like a ladder or something. He holds onto the ladder. He's like, yeah, it's a neat technology. They don't use it all the time. You lose a lot to like friction and turbulence and stuff like that, but it's easy. You don't have to worry about battery technology. Okay. So he's sitting at 200 meters. His kinetic energy is equal to 0. But now he has 196,000 joules of potential energy, which we also write as U. Yes, John, you are correct. When the cannon fires, he immediately gets 196,000 joules of kinetic energy. So we can think about the cannon did work so that W net equaled 196,000 joules from sort of the starting point in the cannon to the final point in the cannon, right? So I'm not going to say the cannon did precisely that amount of work because the cannon also had to lift him up by this amount. So it would be the work done by the cannon plus the work done by gravity, which would be negative mg times the length of the cannon, right, would give us our 196,000 joules. But because this is so short, it's probably about 196,000. Make sense? Yeah, it's good. Okay, so we have, I tend to think of it as energy to remember that this is U. Energy. So he has normal force acting on him in this scenario when he's standing on the ladder, yes. But because he's not moving, neither of those forces are doing any work. So he has gravity and normal. His net force is 0, but he's got this stored up energy. He's like his own tiny battery, right? Then he steps off the ladder. What happens? So this is splat, yeah. Well, first he has to notice, right? This is Wile E. Coyote physics. But yes, so potential energy begins to turn into kinetic. Potential energy turns into kinetic. How does that happen? It happens because gravity does positive work, right? Work is the process of energy transfer. So to make potential energy turn into kinetic, gravity is doing positive work to make this happen. So how much work does gravity do? No idea. Only had really one number so far. Ooh. So this is how much work does gravity do? Let me be specific. On the trip down. Because you were correct. The total work gravity does from the launch to the splat would be 0. Right? There we go. That's what I wanted. 196,000 joules. Right? So if we think about from launch to splat, at the launch, he had 196,000 joules of kinetic energy. That turned into, so as he went up, gravity did negative 196,000 joules of work. Our kinetic energy went to 0. Our potential energy went to 196,000 joules. At the top, on the way down, gravity did positive 196,000 joules. Kinetic energy went back to 196,000 joules. Our potential energy went back to 0. So we have sort of lots of K. K gets lower. At the peak, its kinetic energy is 0. Kinetic energy is getting bigger again, right? And then splat happens. What happens at the splat? Our kinetic energy goes back to 0 because he gets stationary. Energy go, where does the energy go? The ground? So remember, potential energy is energy that you have to get back out. When someone hits the ground, you're not getting that energy back out. You cannot then turn that energy into something. Gets converted, okay? Converted into what? Heat. Energy goes into him. I would say there's probably a little bit of heat, but I think it's more deformation. Right. He gets deformed. Lots of deformation going on here, yep. There's that saying about like you drop a mouse, a person, and a horse from the top of a building. Mouse runs away, human breaks, the horse splashes. It's a lot of deformation going on here. It's a lot of kinetic energy and it's got to go somewhere. Why would the horse have more kinetic energy than the mouse? Same speed. Horse has a lot more mass. Okay. All this making sense so far? Yeah, there you go. Horse has a lot more mass. So the key for these questions is you have to be really specific about when your starting point is and when your ending point is, right? So we're going to get a different answer if we consider right before it hits the ground versus right after it hits the ground, right? Right before it hits the ground, it has tons of kinetic energy. Right after it hits the ground, it's got nothing. Okay. So you might have noticed that we basically just have this one number that we're moving around, right? We have work done by gravity, went to potential, work done by gravity, came out of potential, right? So our work done by gravity is equal to the negative change in our potential energy, right? So when we did, right, so work done by gravity equals negative U final minus U initial, or we can just move our minus sign, U initial minus U final. So when gravity did negative work, our final potential energy was that amount. When gravity did positive work, right? Making sense? All good. So it's a way to think about like where'd the energy go? You do positive work. Positive work means you are sucking out potential energy and turning it into kinetic energy. negative work is you are storing kinetic energy as potential energy. Give me like a thumbs up or like a happy emoji or something to let me know this is making sense. Yay. Okay, that's good. Hurrah. Okay. So can we just go straight to potential energy and not worry about work? Can we make like a formula? Well, there's a smiling guy and then no. Okay. I know, there's mixed messages here, John. Okay. So if our work done by gravity is going to be the force of gravity times the distance traveled times the cosine of the angle between them, right? We can make, right, so here's gravity's always down. So this delta r cosine theta, right? If delta r is upward, we're going to get a negative sign. If delta r is downward, we're going to get a positive 1, right? So what we can do is use h or y. And so h is always positive upward. So essentially what we're doing is we're wrapping delta r and cosine theta into just delta y, right? Except, let's make sure our signs work out. So if our delta r cosine theta, right? Because if we're moving upward, we would get a negative number for cosine theta. So we want to make, so this is going to be positive if moving upward. That makes sense? Okay. So we can make our expression mg delta r cosine theta equals negative delta u. So our mg negative delta y equals negative delta u. Our change in potential energy is equal to mass times gravity times the change in height, where y is positive upward. You might also see this as mgh. I prefer this because it's more focused on the change, because the change is what matters. I think most people have seen this equation before. If you've had any sort of physics class, it's pretty common. So why am I so focused on the change? Well, the basic answer is because that's what matters. If you're just sitting at the same height, it doesn't really matter if you have potential energy or not, right? You're just sitting there. What matters is if your potential energy is changing, then it's like, oh, I am speeding up, I'm slowing down. Also, because 0 is our choice, right? So if I have this guy hanging out on a ladder and he's 200 meters above the ground, oh, I can say his y value is 200. But, okay, what if the ladder is next to a cliff? So it's 200 meters above the ground, but then this is 100 meters deep. Is this 200 or 300? Doesn't matter. Because what matters is when he falls, delta y is negative 300. Right? I can declare that the bottom of the thing is 0, and this is 100, and this is 300. I can declare that his starting point is 0, and then this is negative 200, and this is negative 300. Right? I can declare that this is like, I don't know, I can say he's at 1850 meters. I don't know why the 1850 compromise. I have no idea. But that means that this is going to be 1650 meters, and this is going to be 1550 meters. Does not matter because his delta y is 300. Okay. So far, so good. Yes. Okay. What about if the ladder leads to the top of a water slide? Okay. As he slides down, how much work is gravity doing? Oh, hi, Lon, guys. Welcome back. What is his kinetic energy at the bottom? We're going to say frictionless for our purposes. Need the angle of the water slide. You don't need the angle of the water slide. That's what makes it so wonderful. 196. Gravity is still doing positive or negative. Positive, yes. Good. So here's the trick here. If we want the work done by gravity, it's going to be the force of gravity times the distance traveled times cosine theta. Okay, so let's imagine he's right here. So mg, he's traveling this direction, so that's delta r. So if this angle is theta, then this angle would be 90 minus theta, right? So this would be mg delta r cosine 90 minus the angle of the slide. Okay, but our delta r is not 200 meters. Our delta r is the length of the slide. Okay, how long is the slide? Okay, well, we have a triangle where this is 200 meters, this is theta. Okay, so L is the hypotenuse, so the sine of theta slide is going to equal opposite over adjacent. Okay, remember that the sine of this is the same as the cosine of 90 minus the slide, theta slide, right? The sine of 30 is the same as the cosine of 60. You remember this from trigonometry? Yes, you do. Okay, moving on. So my work done by gravity is mg times the length of the slide times the cosine of 90 minus the angle of the slide. But I can plug this in. This is 200 meters divided by the length of the slide. Oh, hey, look, the length of my slide cancels. And I'm left with mg times, hey, the height of my thing. Mg negative delta y. So my work done by gravity is 196,000. I'm losing 196,000 joules of potential energy. Where did that energy go? Uh-oh. There it is. Where'd it go? He lost 196,000 joules of potential energy. Where'd it go? Turned it in kinetic. So what's his kinetic energy at the bottom? Ooh, careful. 196,000. We're going to presume that he just keeps going horizontally at this same speed, actually, that we found earlier. So this is a fun thing. It doesn't matter. If I asked you, this is an example of a conceptual question you might see on a test, right? Which slide will have you moving faster at the bottom? Option A. There's a ladder. Option B. Pretend that's a straight line. Tremor. Option C. I didn't leave room for option D. Say they're all the same height. H, 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 H. Which slide will have you moving faster at the bottom? I already labeled this D, it doesn't need to be 2. Aha. Ooh. Shannon's right. They're all going to be the same, presuming they're frictionless. If there's friction, it does actually matter how long they are. But if they're frictionless, they will all be the same. This is a trick question. Sorry. Right? Because they all have the same delta Y. So gravity is doing the same amount of work. They have the same amount of starting potential energy and the same amount of ending kinetic energy. All will be the same. Okay. Right? That theta canceled out in our equation. This is making sense? Same work. Same delta U. Same. Okay. Now, one thing is that I've also added like these wobbly bits. It's not a straight line. Same thing for A. A is not a straight line. How does that matter? Well, the answer is, doesn't matter. The line isn't straight. Because if you think about each individual chunk, right, I can choose this individual chunk, and I'm going to call that delta r. And I can do that same thing with theta, and I will get that what matters is this delta y. For this chunk, I can do that same trick with theta, and I will figure out that what matters is this delta y. And then the same with this chunk, and the same with this chunk, and the same with this chunk, right? This is where that idea of the line integral comes in, that you're doing the line integral of gravity over this entire path. And so theta will cancel out for each little chunk, which means that it doesn't matter for the whole thing. Yeah. You only have to look at the beginning and the end, like kinetic energy and work, right? So we only care about y end minus y beginning. We do not care about the path. This is what is called path independence. Yay, long guys. It does not matter which slide you take down, you're going to be going the same speed at the bottom. So next time you go to a water park, it's all about the height of the slide. Right? Now here's an important note. This is only true for what we call conservative forces. What's a conservative force? A conservative force is one that's path independent. Nothing to do with politics. Right? They sort of go together. But conservative forces also have an associated potential energy. Not all forces do, right? So think about forces where you can store energy or get it back out. Right? So obviously gravity is one of them. Can you think of any other forces, like any other situation where you can store energy and then get it back out? A spring, yeah. Springs, elasticity, kind of stuff. A pendulum, yeah. So pendulum is sort of included in gravity because that's the force where you're storing it. Mm-hmm. Can you think of any others? This is a little tricky. How about an actual battery? Electromagnetic forces are also conservative. You will see this in physics too. We're not going to talk about it right now. Yeah, batteries, actual batteries. Right. So these are all conservative. What about some non-conservative forces? Can you think of some examples of non-conservative forces? Trampoline, yeah. A trampoline, it's usually springs. It can also be sort of the elasticity of the material itself, right? Like you can, do I have anything that is squishy near me? Nope. But if you have like a ball or something that you can squish, and then it pops back into place, right? It's not an actual spring, but you're still storing energy in that elasticity, right? So what are some non-conservative forces where you put the energy in and it's just gone? Friction, definitely non-conservative. Energy goes to heat. Friction full slide, yeah. Deforming forces, right? Right? If I squish a ball, it'll pop back into place. If I squish a Coke can, it will not pop back into place, right? The deformative forces, it's just squished, right? I should have squished that and then it'd be really impressive. Squish it. Nope. There we go. Deformative forces. You are not going to get this force back out. Oh, it's not empty. Whoops. Deforming forces. Can you think of any others? Pretty much everything else that we've talked about. I'm going to go a little faster because I do want to finish this. Everything else. So things like tension, normal, like pushing and pulling, right? You are not getting that energy back out. It's just, right? If I push this along some horizontal surface, did I store any energy? No. Magnetism is conservative, yes. Because you can hold two magnets together and then you release them and they pop apart. You have gotten that energy back out. Okay. So let's. So if we look back at these slides, right, and we consider friction, why are only some forces conservative? That is a really interesting question. And I don't know if I can give you a satisfying answer. I want to say that they're mediated in a different way, but I don't know. Because springs, I'm not sure how that's mediated. I don't know. It's an interesting point. I'll look it up. A lot of times the answer is because that's how the universe seems to work, but there might be a deeper answer for this one. Okay, so if we think about these cases, if we include friction, can I like copy these and paste them? Oop, doesn't like that. Copy. Paste. No, apparently not. Apparently not. Whatever. That's okay. So if we have some more slides, they're all the same height. One goes like this. One goes like this. And one goes so I'm trying to have it be there. Which have more energy lost to friction. Actually, let's exclude this one for now because I'm not 100% sure. Third one. More surface area. I wouldn't think of it as surface area. I would think of it as like a longer path. But yeah. So you do have to care about the length of the path. But you also have to care about theta, right? Because our force of friction is mu k times the normal force. Our normal force is mg cosine theta for something on a slope. So our work done by gravity is going to be mu k mg cosine theta slide times the length of the slide times our cosine of the angle between friction and, so this is our delta R. This is our force of friction. Aha, it's always 180 degrees. So that's good. So we end up with mu k mg cosine theta slide times the length of the slide times -1. The length of the slide is going to be the height. Wait, we have sine of theta slide. Sorry, I'm like working this out for myself. Is the opposite over hypotenuse. So L is h over sine theta. So we can plug that in. We get mu k mg times -1 times cosine theta slide times h over sine theta slide. We get a cotangent in here. What? Negative mu k mg delta y cotangent theta slide. Geez, what does the graph of cotangent look like? So you would get your maximum force of friction for your maximum cotangent, which happens, when does the cotangent reach a maximum? Right. Tangent reaches a maximum at pi/2. So cotangent reaches a maximum at 0. So it would be the longer one. Yeah. Longer. And then if we have a wobbly path, right, you would have to integrate this along the whole thing and figure out when this actually integrates to a bigger number. So let me think about this. So you have to, in each little chunk, it's going to be based on the cotangent. So you're going to have more friction, more work done by friction in the flatter parts and less work done by friction in the vertical parts. So you'd have to kind of figure it out. I'm actually not sure. Because the wobblier it is, right, the longer it is for sure. But also there are these sections where it's almost vertical and you have essentially your normal force is very low. So you have very low friction. So I would say this is a non-trivial question. That's why I had to remove it, that option. But in this case, I think you get more friction. More work done by friction. In this case, more energy lost. Okay. Oh, it's 10:45. I really wanted to talk about springs. How many classes do we have left? We have 3 classes left, and I still need to talk about torque. Okay. Will you give me, like, I'm going to talk about springs. If you need to go, you can go. I'm going to, like, cut this out and I think post it as its own video. So here's what I'm going to do. I'm going to stop my stream.